For strain, it's no units. Yeah. Yeah, strain is a ratio, so it's unitless. That's pascals. Okay, so let's start with, before I get into this, um, the exam is next Wednesday. And the topics are everything up through strain and the constitutive relationship. I think the last one, I think it's number 17. I never assigned. You don't have to worry about that. But everything else. And so the way to get ready for the exam is to go back through your daily assigned problems and just make sure you understand how to do all those, that you understand the ideas behind it well enough that you could sort of explain it to someone. If you can do all those, you'll do well on the test. Any questions about the test? Okay, so I'm going to start with number 11 from the homework. So we have a Voigt strain of that's given, and we're told to use the material from number 10. Well, number 10, I don't think specified a material, so. Oh, it does. Okay. Oh, okay. Okay. So let's so number 10. Oh, we did this one last time. Can someone tell me what you got for E and new?
For E is 1 times 10 to 11, and for D is 0.1.
Okay, and new is 0.12. And so you can use this to calculate a compliance matrix. And what we're going to use is the relationship that says, so more often what we use is this. We use that the Voigt strain is equal to the compliance matrix times the Voigt stress. But you can also use the relationship that says the Voigt stress is equal to the stiffness matrix times the Voigt strain. Where the stiffness matrix is the inverse of the compliance. And I think all your calculators will do that inverse for you. So you can enter the compliance matrix however you're used to entering it, and then have your calculator calculate that inverse. And then it's just a matter of, the Voigt stress is just equal to that stiffness matrix times 0, 0, negative 5 times 10 to the minus 5, 0, 2.5 times 10 to the minus 5, 0. And it'll give you the 6 values of the stress. So that'll give you the Voigt stress. And then you just have to reorder it to put it into the stress tensor. And if it asks for the stress cube, you have to do that. Anybody have answers to that you wouldn't mind giving me so I don't have to enter this all into my calculator? What you get for the Voigt stress? I just don't have this compliance program, so I kind of have to enter all the values. I'll do it though. Then you'll be sorry.
704,000 for 5,000.
Okay.
Do you want rounded or what do you want?
Sure. Let's go. I'll do it all times 10 to the 6. So I'll call this 0.705. I'll do it all in megapascals.
Okay, and then negative, and then the same number,
Okay.
and then negative. Because, yeah, negative 5 million,
Okay.
0, and then 1 million.
Okay. So this is all in, well, this is all in megapascals if I get rid of these. Okay. So then the stress tensor is just goes in the order. The first 3 are the main diagonal elements. And then YZ is the next one. XZ is the next one. And then XY. And then make it symmetric. Okay, so there's the stress tensor. And then we want to express this in a coordinate system rotated negative 45 degrees about the y-axis. So our rotation matrix is going to be cosine of negative 45, 0, negative sine of negative 45, 0, 1, 0, positive sine of negative 45, 0, positive cosine of negative 45. The stress tensor that we want is, so the rotated coordinate system is the rotation matrix Q times the stress tensor times Q transpose. So we're going back to principal stresses. And the idea of this is no matter what the state of stress is, there's a coordinate system where that stress only has normal elements. And these include the maximum and minimum possible normal stresses. Um, and from there, it's easy to find the maximum absolute value of shear stress. And so this is finding the principal stresses is a super important part of figuring out whether a material is going to break or not. These are just really important parameters to know to determine whether the material is going to break. So let me first talk about, I'm just going to give you the short, like, how do you calculate this stuff? It's really easy. So this is the take-home message, the too long didn't read message. So let's say that you're given a stress tensor, and I'm going to do this with, so I'm going to do this with 5, -6, 0, -6, 10, 1, 0, 1, -5 in megapascals. So that's just my example. The eigenvalues, I don't know why I wrote that in lowercase, but the eigenvalues give the normal elements of the principal stress. So on a TI 89 or a TI Inspire, the way you do that is you just call the function eigvl, and you do it on whatever matrix you want. So this is going to be 5, -6, 0, -6, 10, 1, 0, 1, -5. And it'll give you, in curly brackets, I just made up this matrix, plugged it into this eigenvalue function, and got 14.036, 1.050, and -5.087. So the principal stress tensor
So what about the TI-84?
it doesn't do it, but I'll tell you how to do it online. You can just use Wolfram Alpha or something. On exams, I'm not going to make you do these unless they're easy to do by hand. So the principal stress tensor would be 14.036, 1.050, negative 5.087, or any other permutation of those. So it could be 1.05, negative 5.87, 14.036 on the diagonal or whatever. They can be in whatever order. That just has to do with what 90-degree rotation the coordinate system is in that you're using. And as far as the maximum and minimum, that this answer says that the maximum, if you tried all the infinite coordinate systems to analyze this original stress tensor, the maximum normal stress you would ever find is 14.036 megapascals, and the minimum you would ever find is negative 5.087 megapascals. That's pretty amazing.
To do this by hand, we would just have to do basic matrix math and just simplify it down, right?
If what?
To do it by hand, you said.
Yeah, so we'll talk about that more later. I think really just on exams, I'm just not going to make you do it. I'll just make you do it in homework. But so notice that what we've done, what the calculator has done, is it's found a stress tensor in some rotated coordinate system. How do we know what that rotated coordinate system is? So what is the principal coordinate system? For that, you use the eigenvector function on an 89 or an Inspire. And that will give you, it'll give it to you in the form 0.553, negative 0.832, negative 0.044. It's actually going to do it in a matrix, not in vectors like this. And then for the second column, 0.832, 0.548, 0.091. And then for the last column, negative 0.051, negative 0.086, 0.995. And what this says is in your original coordinate system, this is the outward facing normal for the first eigenvalue we got. That was 14.036. This is the outward facing normal for the second one we got, which was 1.050. And this is the outward facing normal for the third one, negative 5.087. Normally, you don't need those. There's no reason to know that you care what the coordinate system is. But if you ever needed to know the coordinate system, that's how you would get it. Okay, how would we do this? How would you do this if you don't have a calculator that does eigenvalues? Let's just look at Wolfram alpha. And so I'm going to go in here. I mean, I haven't done this in a year or whatever. I don't remember where you go to do it, but I'm just going to type in eigenvalues. And it brings up a calculator. It says this is the format it wants. That's the first row, second row, third row. So I'm going to type in my 5, -6, 0, -6, 10, 1, -0, 1, -5, and compute. And there's a little round off error probably, but that's basically what I gave you. One thing that's a little annoying that it does is it doesn't give you the eigenvectors as unit vectors, so you have to normalize these yourself to find the unit vectors, but that's not too hard.
Your calculator gave out 1.05 as eigenvalue 2, eigenvalue 2,
Right.
eigenvalue 3 for the other one. Like, does that?
Right. It doesn't matter at all. It's totally arbitrary what order they give them to you. The only thing that matters is that the eigenvectors correspond to the eigenvalues. So notice if we, so let me do, my first one was 14.036. And so let me do one of the ones that's different. So -5.087 was my third eigenvalue. So that should correspond to my third eigenvector of -0.051, -0.086, 0.995. So I'm going to type in their corresponding eigenvector for that, and you'll see that it matches my third eigenvector, not my second eigenvector. So -0.052, -0.087, and 1. And then I'm going to take a unit vector in that direction. And I get -0.052, I guess I got, just round off here, -0.087, 0.995. They can come out positive or negative too. That doesn't, you can multiply by -1, but so that's how it works. Each eigenvector has a corresponding eigenvalue, but it doesn't matter what order you put the list in. I'm sure you could also just go to ChatGPT and ask it to, you know.
There's another website I used. I didn't use it when I was in top 4. I used some help or something.
Okay.
Some other website.
Yeah.
Same thing.
Yeah. I'm sure there's 100 websites that'll calculate eigenvalues and eigenvectors for you.
Mostly because it can help me verify my steps I've taken to get the eigenvalue.
Mhm.
Since it's step by step.
Yeah. Okay, so okay. This is not the way that principal stresses are taught in the traditional Deform textbooks. So in the traditional deform text. Come on. This is done using something called Moore's circle. So if you ever, once you transfer, you take a class and they have you do some kind of review where they ask you to use Moore's circle, just hand them this note. This is a note from me giving you permission. It says, I use eigenvalues and eigenvectors because they have electronic digital calculators now. So, okay, they still teach Moore's circle, but it's a totally useless thing that you would never use in a company or in a research project or anything. So tell them to stuff it. Once you have your three principal stresses.
Wait, so they get mad at me, can I send them your?
Yeah, just send them my number. Yeah, I'll talk to them. Once you have the three principal stresses, and those will be, we'll have sigma max, sigma mid, and sigma min. Then the maximum possible shear stress, tau max, is just equal to sigma max minus sigma min divided by 2. Okay, so like for the example before, I got these three, where are they? I got these three eigenvalues. Oh, wrong day. 14.036, 1.050, negative 5.087. So the maximum possible shear stress in absolute value is 14.036 minus negative 5.087 divided by 2. So 14.036 minus negative 5.087 divided by 2. And so that's 9.56 megapascals. And what that says is if you again did the stress transformations to all the infinitely many possible orientations of a coordinate system, the biggest absolute value shear stress that you would find would be 9.56. It could be negative or positive, but that's the biggest absolute value. God dang it. I put this on the wrong day. Okay, I got to correct this. How long had I been doing that? There's one thing that Moore's circle allows you to do that this doesn't. I mean, it allows you to, but it's not very natural. It's a totally useless thing. There's no reason you would ever want to know that, but sometimes people ask it if they're using Moore's circle. So, um, and that's figuring out if you have, if the principal stress is just a single rotation, the principal coordinate system is just a single planar rotation of the coordinate system. Moore's circle makes it easy to see what the angle was. So this is not something that's useful for engineering in any way, but I'm going to show you how to do this. So let's say that we have, so our example is a stress tensor that we're starting with of negative 5.3310, negative 0.743, 0.80, negative 0.743, negative 6.669 in megapascals. So what's the angle of rotation to the principal coordinate system? And it's really just thinking about it geometrically, knowing that you're given the coordinate axes. So if you calculate the eigenvalues, it gives you negative 5, negative 7, 8. And if you calculate the eigenvectors, it gives you 0.914, negative 0.407, 0.407, 0.914, and then third 010. And all you have to do is ignore the one that hasn't changed. And calculate the angle change from the other two. Okay, so if this is our original coordinate system, our new coordinate system is positive 0.914, negative 0.407. So one axis is like this. And the other one is positive 0.407, positive 0.914. So the other axis is like this. We're trying to figure out this angle. And so you can just do inverse cosine of 0.914. And it gives you 24 degrees. We rotated clockwise, so we want ours is the negative. Okay, it's just a little bit of geometric thinking. Like I said, there's no engineering reason that that would be useful, but you can do it. Um, okay.
So there will only be like, what happens if there's more than one angle? Like, please ignore the one that hasn't changed. What happens if that one did change?
So what if there's more than one angle? Then it gets complicated on how you do your angles, like which one you do first, which one you do next. There's not a simple answer to there's really only a simple answer to what the rotation is if you only do one of them. Okay, well let's just get used to this idea. So I'm going to write up this example, and you can either, if you have a calculator that does it, you can use that. If you don't, you can use your phone. But let's say that we have a stress tensor of -7, -2, 4, -2, 10, 0, 4, 0, -8 megapascals. And we want to calculate the maximum and the minimum normal stresses and the maximum absolute value of shear stress. Okay, so what I got was my principal stresses are -11.61, -3.63, and 10.24. Anyone get that?
Yeah, that's
Okay. And I'm sure some of you got them in different orders, but the order doesn't matter. Did anyone get anything different? I mean, the only way you could get something different, I think, is to enter the matrix in wrong.
I forgot negative.
Okay, yeah.
The one was wrong.
Here's a question that goes all the way back to the matrix math, something that I sort of mentioned in passing in matrix math. What would happen if you calculated these eigenvalues and the matrix that you entered was mistakenly, like you typed it in wrong, and you didn't put in a symmetric matrix? So the eigenvalues of a matrix that's not symmetric, remember stress tensors are always symmetric matrices. The eigenvalues of a matrix that's not symmetric in general are complex. Okay, so if you ever see complex answers come out in your eigenvalues, it means that you entered a matrix in that wasn't symmetric. And so that's a easy mistake to make and an easy mistake to find. Okay, so now what I asked for was the max and the min and the maximum shear stress. So which of these is the maximum? 10.24. Yep. So the key thing here is that you have to take the signs into account. Okay, so sigma max is 10.24. So then what's sigma min?
11.
Yep, negative 11.61. And then the absolute value of the max shear stress is 10.24 minus negative 11.61 divided by 2. And so that is 10.93 about. So if you did a million different coordinate system transformations to all these different orientations of this matrix, you would never find any shear stresses with an absolute value bigger than that. Okay, here's another one. So let's say that our stress tensor is 5, 0, 0, 0, negative 7, 0, 0, 0, 9. Answer those same questions. What's sigma max, sigma min, and the maximum shear stress? And if you're smart and you realize everyone else is doing stuff that you don't have to do, just sit there and feel smug. Notice that this is already a principal stress because all we have are normal stresses.
So if there are no shears, then it's automatically
Right, if there are no shear stresses, then you have a principal stress tensor already. And so you can just look at it right away and say sigma max is 9, sigma min is negative 7, and the maximum absolute value of shear stress is, right, yep, 9 minus negative 7 divided by 2, so 8 megapascals. Um, okay, what if, it's a little hard for me to think of practical applications where you would want this, but what if instead of just the maximum absolute value of shear stress, you wanted a stress tensor that contained that absolute value of shear stress? So what if you wanted a stress tensor containing the maximum absolute value of shear stress? The way to do that is start with a principal stress tensor. And then rotate the coordinate system 45 degrees about the axis with sigma mid. Okay, so for example, I'll use my example above. Um, so my sigma was 5, -7, 9. So 5, -7, 9. The max is 9, the min is -7, so the mid is 5. And that's associated with the x-axis, just the way I have it in this coordinate system, in this stress tensor. And so I'm going to rotate 45 degrees about the x-axis. So my Q is, I'm rotating about x, so this is going to be 1, 0, 0, 0, cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45. And my new stress tensor is going to be Q times my original stress tensor times Q transpose. And what I get is 5, 0, 0, 0, 1, 8, 0, 8, 1. And that 8 could have showed up as a -8. It's an absolute value thing, but you can see that what we had predicted was going to be the maximum possible absolute value of shear stress shows up in this tensor. Okay. One way that this comes up, so one surprising way this comes up is in the fractures of brittle materials in compression. Okay, let's say that we have, let's think of it as like bone is a brittle material. This comes up a lot of times in leg fractures and car accidents. So let's think about what happens in a compression fracture from a car accident. So you have forces acting like this on the two ends of your femur or whatever bone it is. So the corresponding stress tensor, if we think of this as a stress cube, you could think of a value like this. Okay, and I'll just call it sigma. It's just some sigma value. And so the stress tensor, in this case, I have it in the y direction. So this would be 0, 0, 0, 0. This would be negative. So 0, negative sigma, 0, 0, 0, 0. Right, that's the stress tensor. Okay, what would you get if you calculated the eigenvalues of that matrix? You'd get the same thing, I mean, you'd get this same matrix back. We're assuming that this is some number, we just don't know, because this is already a principal stress tensor because there's no shear stresses. Okay. So this is already principal. And so let's think about the max and min and mid stresses. So the max is 0. The mid is 0. I'm just reading the values off the main diagonal. And the minimum is negative sigma. Okay. And so the maximum value of the shear stress would be 0 minus negative sigma over 2. So that's just sigma over 2. And now let's think about the rotation of the coordinate system that you would need to have a coordinate system, to have a stress tensor where that maximum shear stress showed up. So we're starting in a principal coordinate system. We're going to rotate 45 degrees about the middle eigenvalue. So that could be the x or the z. Okay. So let's think about it. I think it's a little easier to think about it in terms of the z. So a principal coordinate system would be something like this. Okay. And when you get these compression fractures, they're recognizable as compression fractures because this is what they look like. There's the bone, and the fracture goes one way or the other, broken straight along a 45-degree angle. So since bones are brittle materials, and they're most likely to fail in shear before they fail in any other type of loading, they break along a surface that has the maximum shear stress. So bones in compression break along a surface with maximum shear stress. And that's just a reliable fact that orthopedic surgeons know very well. They see a bone like that, they know what happened. But it all has to do with the relationship between maximum normal stresses and maximum shear stresses. Okay. Anybody have any questions? Okay, that's it for today.